So today, it's my pleasure to present our official host of seminar, Dr. Ashna Ghanbari. So Ashna did her master and PhD under Benno's supervision. And most of them being here around, she's a tennis player, good-playing tennis player that I know we have to play someday.
Yes, for sure.
And a coffee lover, of course. And she got married last year, and I went to her home, beautiful house. So, and amazing food. So today, Dr. Ashna will talk about from gait to pain, evolving question in running biomechanics. Okay, Ashna.
Thank you, Mark. So obviously being the moderator and the introducing person in our HPL seminars for the past 2 years, I can't not introduce myself. I have to do it. I don't need an introduction probably at this point, most of you know me, but I'm just gonna go a little bit deeper and hopefully you know me a little bit better after this intro. So I was born in India. I went to high school in India as well, so I lived there all the way up until I finished high school. And somewhere along my life in India, I started playing tennis and I really fell in love with the sport. Most of my time was spent in training and trying to be the best version I could and hopefully become a professional tennis player one day. That was the dream and the goal. But dreams and goals always don't go the way we expect. I got injured somewhere down the line and then never could really come back to pre-injury levels. But what I had to do somewhere in that process was figure out what I want to do with my life next now that I can't play tennis as a professional. So in India, when you're going into high school, you have to make a decision on what your career is going to look like in 50 years and basically pick your stream of study. So you either choose science, you choose finance or economics, and you choose arts, and that's it. You can't really go back. So I was like, okay, what can I do with my life? I looked up a lot of careers that are related to sport because I didn't really know anything other than that, and I love sports. So I was like, what can I do with my life and pick a career in it? And I found biomechanics. And I really liked the idea of being the sports biomechanics specialist for United or Roger Federer. And I was dreaming big and I wanted to do it. So the next goal was to figure out where I can go study biomechanics because that wasn't a program offered in India. So I started looking up all the best schools that offer the program and where I can do some research that can help me prep myself for this big goal. So I came to U Calgary and started my undergrad in biomechanics. And then in the final year of my undergrad, I had to look for a lab where I wanted to do my final year research project. And I came to Dr. Benno and asked if I could do that internship. Long story short, I was told no, but I managed to stick around and get a yes, and finally did a study that was looking at the effects of shoe upper construction on lateral movements given my love for tennis. I also started liking the HPL a lot, and I said, okay, I want to do more research here, and I started a master's in 2020, and soon after that, fast-tracked that into a PhD, and started looking at footwear-specific biomechanics that I'll talk about later today. Finished up my PhD in 2024, and then I started a postdoc here, as well as a consulting part-time role at a company called Plantiga for 1 year, where I was basically working with a wearable tech startup from Vancouver and working with some really elite high-profile athletes. That was a really cool part of this consulting job, and I got to work with them to understand how they use wearable technology and biomechanics data to inform certain decisions. I've since been here as a postdoc, and now I'm also teaching part-time at MRU. But the one fun fact about me that I wanted to share is that I really like pictures, and I like showing pictures and taking them. So I'll share my fun facts through pictures. That's me on the left playing tennis in India, and then that's me on the right in the whole Dinos tennis team, which was a really fun part of undergrad. I did play Dinos tennis, traveled with the team, got to spend some fun times competing. And as Mauro said, I got married last year, but this is another fun fact that I like to share. At some point in my PhD, I decided it would be a great idea to build my home, plan my wedding, and finish my thesis all in the same year. Would not recommend, because I spent a lot of days feeling like this, but we got through it. And today, here we are, put all that on that slide, and I'm going to focus on my PhD and postdoc, specifically for today's talk. So when we talk about running and running research in general or running performance, one of the terms that we see thrown out a lot is advanced footwear technology since the last few years. And advanced footwear technology, or shoes, AFTs, specifically look like the ones on the slides here, and are a big, big part of talking about long distance running, winning races, and running fast. But what does AFT really mean? What is it? AFTs are performance enhancing footwear technology that combine lightweight, resilient midsole foams with rigid moderators and pronounced rocker profile. Fancy words for just saying that they have highly compliant and resilient foams and a stiffening element like a curved carbon fiber plate embedded in them, and have a curvature in that forefoot part. One of the most common AFTs that we've talked about in the past few years and in this lab as well is the Nike Vaporfly 4% shoe. That's the shoe there, and then it's the blown out picture of it, of the different parts of the shoe. And specifically, we have a PIVA midsole foam, which is that highly resilient and compliant material. And then we have a curved carbon fiber plate embedded in between those two foam pieces, and a toe curvature that then defines our AFT. The shoe got really popular when in 2018, a study came out of the Hukamer lab where they tested energy cost of running, which is shown on the y-axis here, and basically had runners perform running trials at different speeds in 3 different shoe conditions, the Vaporfly and 2 competitors at the time, very good shoes, and basically found that energy cost of running can be reduced on average by 4% at different speeds in these Vaporfly shoes. They got more popular when we saw runners breaking records in them. We've seen lots of records being broken, specifically also Kipchoge running the under 2-hour marathon in 2019, also wearing those shoes. And so moving forward in this AFT space and post-Vaporfly research, we started seeing a lot of studies come out that were talking about the energy cost of running in marathon running shoes, the effects of certain parts of these shoes, like longitudinal bending stiffness and the running economy, as well as the metabolic cost of running or energy cost of running on level, uphill, downhill, and different shoe conditions being tested. Studies were coming out, but the one part they were forgetting to address or skipping is the fact that we're not able to explain these observed performance improvements mechanically. What are the biomechanics that are really happening when we have people run in these shoes that improve their running performance? And the other problem was that people were testing different shoes. Like you saw in the previous study, they were comparing it to competitor products. And the problem there becomes when it's not systematic, we don't know whether the results that we're getting are due to certain parts of the shoe, are they consistent across studies, and so on. So it's hard to answer how we go from having people run in a shoe to breaking records and improving performance. Which is what brought me to my overarching objective of my PhD study, which was to investigate the effects of advanced footwear technology, shoe features, specifically 2 that I will talk about, on running energetics, as well as exploring the potential underlying mechanisms that improve these performances. When I say 2 specific features, I'm talking about the curved carbon fiber plate in these shoes and the PIVA midsole foam. So the first step in my PhD was to start playing around with prototypes that I was trying to cut and create in order to basically get versions of this shoe that change only one aspect. So I'm trying to remove the carbon fiber plate, and I'm trying to change the PIVA foam with an EVA, which is less resilient, and see whether these systematic changes affect performance. So after lots of prototypes, as well as getting help from a company that runs out of Calgary, I was able to come up with 3 shoe conditions, the original being the Nike Vaporfly, and then the no plate condition in the middle, which basically I've traced the line to show you how the carbon fiber plate runs in that shoe. But we cut it out, we removed it, and we glued the sole back to just reduce the bending stiffness. And then the third condition being the EVA, where we replaced the PIVA foam with 2 pieces of EVA, trying to maximize the amount of EVA we have in there, and also keeping the curved plate in the same configuration as the original. From there, my first objective, or my first study, was interested in looking at the effects of these 2 features on the energy cost of running and muscle activation. So the rationale here was that if muscle activation and force production from your muscles goes up, there's an increase in the muscle energy cost of running, and then there's also an increase in the energy expenditure. So if we can reduce the muscle activation of groups like the triceps or muscle group, we may be able to improve running performance, and that may be what is happening in these advanced footwear technology shoes, because those muscle groups contribute to quite a bit of whole body metabolic energy expenditure. So we hypothesized that removing the curved carbon fiber plate and the PBUF foam would increase the energy cost of running, so you're using more energy to run, but also increase the muscle activation, which may be driving that cost to go up. We had 15 male runners come into the lab, perform a baseline test to determine their speed at lactate threshold, and then have them actually perform the tests in 3 shoe conditions, the original, no plate, and EVA, at 90% of that speed at lactate threshold. And then we used the metabolic cart and surface EMG equipment in order to determine the energy cost of running as well as the intensity of muscle activation in these 3 conditions. The first result that we started with is whether energy cost of running changes when we change these 2 shoe features. And on the y-axis here, you see the energy cost of running. And on the x, you see the 3 shoe conditions I tested, with the original being in the middle. And you can notice that it is always the lowest energy cost of running compared to the 2 shoes on either side. So when we get rid of the curved plate and go to the no plate condition, we on average increase the energy cost of running by about 1.9%. And if we change the highly compliant and resilient foam and go to the right, we increase that energy cost by about 2.2% on average. So not only are we seeing that AFTs improve performance, we are now starting to get an idea of how much parts of that AFT improve performance. Next up is to look at whether muscle activation changes relate to that energy cost of running. But bummer here, we didn't really find any consistent results with muscle activation when going from one or the other condition. So what you're seeing on the right now is the Soleus intensity difference, so percent muscle activation intensity, changing going from original to the no plate condition, or at the bottom, original to the EVA condition. And if you go higher than the 0 line on that graph, you're basically increasing muscle activation going into the modified condition. And if you go lower than the 0 in the negative part, you're decreasing muscle activation. And in the red band, there's no change. So you can see that mostly people have either no change or they're going up and down. And essentially, there's no consistency in what we're seeing in those muscle activation values. And I also tested the gastrocnemius medialis muscle, and we see kind of the same story happen again. Either there's no change or there's inconsistencies in how people react. So we summarized from this first study that curved carbon fiber plate and the PBA midsole foam reduce the energy cost of running, so they help improve performance. But muscle activation, at least measured by surface EMG, cannot answer why we're improving that energy cost. Since then, there have been some studies that have still, again, looked at AFTs and traditional shoes. There have been some indication on lower activation during push-off in these AFTs, but again, we have no change in the total activation or no metabolic measurements to really understand if this is what is driving performance. So PhD is not done. I still need to answer what's going on with these shoes. I get the study too. And I try to look at something that is a little less traditional in terms of the variables we're measuring. In 2020, Dr. Neg and co-authors proposed this teeter-totter theory, which basically said that AFTs have a unique design with those different features that we've looked at in the past few slides. And essentially, these create a class 1 lever mechanism such that the shoe acts like a teeter-totter. Essentially, you push down on the front of the shoe, anterior to the pivot axis, and the back of the shoe is going to go up because it's stiff and rigid. And if this teeter-totter motion does occur, then producing a reaction force at the heel is something that we would see, and this reaction force in the heel may increase propulsion and help runners run more efficiently. The problem being that at the time this was a theory, there was no really experimental data backing it up, and we didn't know how to measure it. So the first part of the study became to understand how can we measure the teeter-totter effect in real experimental data. So we started by getting male recreational runners into the lab again and having them perform overground running, now in 2 conditions, which are the AFT, has a curved teeter-totter or lever-like construction, and then a flat shoe, which should essentially eliminate that teeter-totter. And then had plantar pressure insoles to measure pressure distribution as well as the change in COP. And then at the end, try to understand how angular impulse changes over stance or in that propulsion phase. So what does that variable really mean and how did I calculate that? Essentially, we started with the planetary pressure data that we collected during the running trials and calculated a sum of all of the forces posterior to a pivot axis, which is just that blue dot on the vaporfly in the left, basically visually the point that you can pivot about. So taking that pivot axis, taking the sum of the forces behind it, and finding the location of the sum of those forces relative to the pivot axis and calculating the moment of propulsion. From there, I was interested in knowing what part of this stance phase are we really interested in to know what happens with the moment of propulsion. And that stance phase was when my posterior part of the shoe is no longer in contact with the ground. I don't want forces coming from ground contact, but rather a reaction force. So with our high-speed video camera data, we determined that was from 65 to 95% of stance. And then looking at our results, on that y-axis in the left curve, you have moment of propulsion, which is the variable I just described, and then 65 to 95% of stance phase on the x-axis in the original vaporfly condition, the blue curve, and the control flat condition. So what you can see there is that the orange curve, which is the control flat shoe, is much lower than the vaporfly. But we also want not just observational results, but also statistical significance or numbers that we can basically make sense of. So on the right, you have the area under these curves, which is then the angular impulse in those two shoe conditions for all 15 subjects that were collected in the study, and the average with the solid black line. These, you can see that all 15 participants showed a decrease in that flat condition, so there's less angular impulse, and also this was significant. So we answered, or we found a way to measure this in an experiment, and we also figured out that if it's a flat shoe that does not act like a teeter-totter, we do have a reduction in this variable. We can measure it. But what we didn't answer is what happens with the specific features of the vaporfly. So the next study became to understand what happens when we change those two features on this variable that we've just worked on in the previous study. So based on the results we found in the previous study, we hypothesized that if there's a reduction in the angular impulse and propulsion moment in a flat shoe, that would also happen if we remove the curved carbon fiber plate. Because the stiff plate is what allows that curvature to be used in an optimal manner to pivot about that axis. So if we remove that stiffening element and let the midsole be more compliant and less rigid, we would potentially decrease the amount of angular impulse. We didn't expect a difference with the PIVA foam or the EVA because in that case, you're not really changing that curvature that you need for the teeter-totter, but rather just the foam properties. So again, we had runners come into the lab, kind of do the same type of methodology, so I'm not going to repeat a lot of it. But in this case, again, we have the same three shoe conditions that we saw before, the modified versions of the vaporfly. And then now we're measuring pressure insole data to capture our teeter-totter variable, as well as our metabolic cart data to know whether there's a relationship between these teeter-totter variables and the energy cost of running. This graph should look familiar. It's the same thing, the propulsion moment on the y-axis now, and 65 to 95% of stance on the x-axis. Now the three shoe conditions, the original, no plate, and EVA. And we can see that our first hypothesis that the no plate condition would have a lower propulsion moment is actually confirmed from this graph. There is a 30% reduction. But again, we want to look at whether that reduction and that change relates to energy cost of running. So now what we do on the right-hand side curve here is on the x-axis, we plot our angular impulse, which is just the area under the curves on the left. And then we plot the energy cost of running on the y-axis for each of our 15 participants. So now what we're seeing here is when you move to the right on the x-axis, you're increasing the propulsion moment or the angular impulse, meaning that teeter-totter lever-like mechanism. And then when you increase that, you also go down on the y-axis, decreasing the energy cost of running. And that is true for 13 out of 15 of these participants plotted on this graph. Also being statistically significant and a strong relationship when we run stats on it. So we summarize from these two studies that the teeter-totter effect was something that is greater in shoes with curved carbon fiber plates, and it may help improve running performance or explain those running performance improvements in AFTs. But again, I don't think it answers the whole picture. It may be a part of what is contributing to performance. So I still wanted to keep looking at certain variables that can help explain the full picture. Before I go into my last study, I also want to mention that there were some big limitations that were highlighted during my publication of the first couple of studies in the teeter-totter work, and these limitations were fair and very relevant. So there are limitations such as using a static pivot point to calculate the forces behind the pivot point. Essentially, static meaning the pivot point is the exact same throughout the stand space. That was an assumption in my first model. That may not be true, and we know it is not true because when someone progresses through stance, their center of pressure or application of force changes and goes anteriorly. So that pivot point is going to be more dynamic than it is static. And then a second limitation was that there was no free body diagram in my work to try and explain how changes in this variable that we defined and basically measured in the last two studies, and then being able to use that free body diagram to connect how changes in this variable relate to variables like muscle force that can actually make more sense in terms of energy cost of running. Oops. And since then, we've had a visiting student, Ariana, work in our lab and work on basically trying to address these three limitations from the previous work. And we've made quite a bit of progress with the first two. I'm hoping at some point she will share her work and share the most up-to-date results. Okay, so like I said, I wanted to go through the process and see whether there are other variables that can help explain this energy cost of running improvement. So that brings me to my fourth and final PhD study, which was to see the effects of these two selected features, the same ones we've been going over in the past few studies, and understand whether there's a change in lower limb joint work. So lower limb joint work, or essentially this idea and concept of trying to measure this variable, comes from the fact that in 2022, Matijevich and co-authors put together this framework of distal rear foot power, or foot plus footwear work, which is essentially the area under the curve of these foot plus footwear power curves that you're seeing on the graph, and showed that in advanced shoes that have rigid components and highly compliant and resilient components like the foam, we can increase the amount of work that is done by the foot and shoe complex. And what that means is if we can increase that amount of work that is done by the foot and shoe together, we may be able to decrease the amount of work that is done by joints like the ankle. So the hypothesis in this study became that taking away the curved carbon fiber plate and getting rid of the PWM insole foam, changing it with an ABA would decrease the amount of foot and shoe work. And because of a decrease in that, there would be an increase in the amount of work that has to come from joints like the MTP or ankle joint. Last time you're seeing this method slide for my PhD. But again, we had 17 male runners now come into the lab, perform overground running trials in 3 shoe conditions, the same ones we've seen before, but now we captured 3-dimensional motion capture data and 3-dimensional force platform data to calculate our joint work at the MTP, ankle, knee, and hip, as well as foot plus footwear, or that foot and shoe work. So our first graph here basically highlights the foot plus footwear work, power on the y-axis. And essentially we're interested in seeing whether the area under those curves is changing when we change the different shoe conditions. So specifically in the first part of that stance phase, when we get rid of the plate and go to the orange curve, we see that that area under the curve is smaller, meaning that the foot and shoe are basically storing less energy in that first half of stance phase. Right? While we didn't see a change in the positive side of the graph there, which we would expect if you're storing less energy that you may return less, we did see a shift in the timing of that curve. So you can see that that peak here is a little bit earlier in the no plate condition than the original vaporfly condition. But what gets really interesting is when we look at the MTP here and then the ankle joint here, because we're interested in seeing whether we can reduce the amount of work required at those joints in the AFTs. So in the MTP curve, what we see is that there's more energy lost in that first bit of the curve, And then there's less amount of work that can be done by the MTP joint without that plate in the vaporfly. And because we're reducing the amount of work that can come from the MTP, we are also increasing the amount of work that has to be done by the ankle joint. So having to do more work at the ankle joint, bigger joint, we would think you're getting more inefficient in running. We also looked at the PIBA versus EVA, obviously, and here now you have the black curve being the original, and then the blue curve being the EVA condition. And we're seeing the same curve, the foot plus footwear power, but what we see here is a decrease in the amount of energy that is returned in later stances. So when we remove that highly compliant and resilient midsole foam, we get less amount of return in propulsion phase. And again, if the shoe and foot are doing less together, we would expect that that goes up and is reflected in the MTP and ankle joints. But while visually that is the case, the consistency in these results was not there across the participants. So statistically, there was no change from the original to the EVA condition. Okay, so summarizing this last study, lots of variables, lots of graphs that we looked at, but essentially what they told us is that curved carbon fiber plate in an AFT reduces the amount of energy lost at the MTP joint, increases the amount of work that can be done in the energy lost at the MTP, increases the amount of work that can be done at the MTP to propel the runner forward, and then decreases the work that needs to come from the ankle to do the same thing. And then lastly, with the PIBA foam, the only consistent result we found was the change in the energy return with that PIBA foam being in there. The joint level differences were not consistent across the participants. Okay, what did I take away from my PhD? Lots of work that was done, but I just wanted to spend some time just tying it all together and what that means for AFTs and what we understood about that. So we started with performance and we understood that the two features, the vaporfly, in the vaporfly being the curved carbon fiber plate and the PIBA foam, do individually contribute to running performance and by about 2% on average. The mechanisms that we were trying to understand also started getting highlighted. While not giving us the full picture, we started to understand what may be going on with these shoes. EMG wasn't the answer, or at least couldn't be collected in a way that could answer the question, but we did find that the curved plate increases the angular impulse, redistributes joint work, allows the MTP to do more, ankle to do less, and then the PIBA midsole increases the amount of energy returned. There's obviously been a lot more research in the AFT side now with systematic changes and more extensive studies looking at answering more of the mechanisms. I was in no way the only one that was trying to answer these questions. There was lots of work going on, but they're kind of telling us a similar story where they're all finding a 2%, 1 point something percent change with those two features. And we now definitely understand these shoes better than we did before. Quick sidetrack, PhD takeaway. My 16-year-old beagle at the time started struggling to really walk on my parents' new hardwood floor. And being a shoe biomechanist, I was like, well, I'm going to solve all the world's problems with shoes. And so I just got these rubber boots for my dog and put them on him, and he could walk around and was running around for another 1 year. And we lost him when he was 17. So that was a cool PhD takeaway as well. But coming back to the point and jokes aside, I don't know how many of you know this, but a lot of the work, well, all of the work that I did at least was focused on males. I had male participants come into the lab and perform all these experiments. And that is not just true for my studies. Biomechanics research historically has been built on male participants, and we have limited knowledge or insight on the female athletes. And while this trend is shifting, the focus is definitely shifting. Journals want us to have more publications with females included. We've definitely seen the shift in the HPL itself. There's a lot more female-centric work going on, but this all across globally, this work is still quite focused on replicating male-based studies in females and trying to understand what happens in females, essentially. But as a female athlete, my focus moving forward was to shift my research towards questions that directly address the female athlete. And obviously, the first point here is an observation, having been in the field for a few years now. But again, we like to put numbers to things. We like to back data up with, statements up with data. So I started looking at, in the first little bit of my postdoc work, now I've shifted from PhD to postdoc, started that, so stay with me. And I started looking into what I should study for my postdoc. And the first little bit is just doing a literature review. So I started looking at systematic reviews that highlight whether there is a difference between research done on males and females. So this first study looked at a combination of search terms, so in this case, rugby plus injury or soccer plus injury, and tried to find how many results were returned with these search terms and plotted the distribution of males versus female studies. So the thing you can see in both of these pie charts is that the male pie, which is the orange one, is much bigger than the females. Not just the case in this one systematic review. I looked at another one that looked at publications that were part of the sports medicine journals in 2017 all the way up until 2021. And now we have increased the sports that are presented on this graph. So basketball, soccer, rugby, baseball, softball. And again, we can see that that blue pie consistently stays the biggest. And then just to include other topics as well, let's just go to nutrition and supplements. We're all interested in different parts of sports, not just biomechanics. So if we start looking at the number of studies published in sport nutrition and supplement journals, on the y-axis being the number of publications, and x-axis being the year where they were published, you can see that the amount of publications has really, really gone up over the years. But the one thing that hasn't is the purple bars there, which is based on females. And then lastly, just to drive that point home, I looked at female representation in research published in 6 sport and exercise journals between 2014 and 2020. And the first stat I found in there was that the percent of total studies conducted on females is 6%. Not shocking. We've seen that that is the trend going on in the last few studies. But the shocking one for me here was that the percent of studies that were conducted on males that actually needed to be conducted on males was 0.6%. So 99.4% of the studies did not need to study male-specific stuff. They just, out of convenience, selected that. And I've been part of that problem. We have shoe sizes that are only available in males. I did all of my research there, but now I want to be part of the solution as well. So the current approach clearly is failing the female athlete. We're going from studies that are done on males, coming up with interventions and hoping for the best outcome for the female athlete. That is not happening. We know that is not the case. And let me show you another example of highlighting that. Staying consistent with the theme of our talk today, my PhD, my postdoc, running. Let's take running, for example. It has gone up in popularity immensely over the years. Start with 1970 on the top there. The first New York City Marathon had just about 50 finishers. And then fast forward to 2024, we've had over 50,000 finishers. So running has become very popular. There's no argument there. Running is also very, very high risk when it comes to injuries. Approximately 50% of runners experience injury yearly. And not only that, when we look at females in running, they also experience injuries more than males do. So on the y-axis here, you have injured runners that were prospectively tracked in a study that had 386 participants, and basically found that the number of females that got injured were 100 more than the number of males that got injured. This study was combined data, so there's no really dividing it up with what kind of injury this was. So let's just make sure that that is the case across different types of running injuries. So a study here done in 2002 prospectively tracked about over 2,000 runners, but then grouped the 10 most common injuries for 635 of those runners on this pie chart here. So you're seeing the 10 most common injuries, and then the number next to it is the percent or the injury incidence in this case. I'm going to take 4 of the most common ones because it's a crowded slide. I just want to make it a bit clear. So let's take tibial stress syndrome, stress fractures, PFPS, and ITB syndrome. And look at whether males got more injured or females. For all 4 of those studies, females are at a higher risk of developing these injuries. So what we know so far is that females are understudied, and running comes with a high risk of injury, which is even greater for the females. What we don't understand is the mechanism of that injury, so we can't really make any conclusions or suggestions as to how females can reduce that injury risk. And that's where I'm trying to set up a prospective, holistic study in my postdoc that looks at understanding running injuries in female athletes. So that's what's in the middle here of this big picture framework. And then we think of all of the different things that can affect this injury risk in the female athlete. And we put those bubbles all around that prospective study. And this is kind of set up in a way that we want to mimic this, multidisciplinary, holistic approach that goes on in the HPL. But also, while this is really cool and vast, we also have to start somewhere. So I'm going to share 2 examples of the studies that I've designed in the last couple of months. And the point of this is to share it in its early stages so that I can get some discussion started and feedback on what I can do better to answer these questions. So we're starting with hormones. That's the one that's highlighted here. We know that there are certain hormonal fluctuations throughout the cycle, menstrual cycle of the female. So on the y-axis, you see hormone levels, and then on the x-axis, you see the days in the menstrual cycle. And the different colored curves essentially are telling you the most common hormones that are fluctuating during the menstrual cycle. And what you want to pay attention to is progesterone and estrogen, which are the purple and yellow lines, which are really, really high in this luteal phase, and slightly high here with estrogen around ovulation. So we know that menstrual cycle affects hormone fluctuations. Studies have shown that hormone levels also affect something called joint laxity. Essentially, joint laxity is how much translation there is in your joint. So for example, anterior tibial translation, how much your tibia moves anteriorly. If it moves more, there's more laxity. And these are related to changes in hormones. So high estrogen levels relate to high joint laxity levels, as well as progesterone. That hormone that is really high during the luteal phase is also shown to affect joint laxity and increase knee laxity. And people have also tried to understand whether with those hormonal fluctuations, there are biomechanical differences in certain variables that we're used to measuring, like peak knee valgus, hip abduction moment, rear foot eversion, and inversion. So what's done so far is that laxity has been related to changes in biomechanics as well as hormones. There are certain biomechanical variables that have been measured, and we have shown that laxity indirectly can alter mechanics during certain tasks. But what is not known is what is this effect in running. Specifically in running, no one has looked at whether laxity affects running biomechanics. And then the variables that are often studied in these papers are not necessarily linked to high injury risk. And so that link between laxity, mechanics, and injury is not super strong. One, because most studies are retrospective, and second, they either just didn't do it holistically or measured one part of the question. So with this first study, the objective is to determine whether changes in joint laxity across the menstrual cycle are associated with altered running biomechanics, and potentially, as a sub-objective, test whether a joint support or bracing intervention, if we do find changes in mechanics with laxity, can those interventions improve that during running? And our hypothesis is that it will increase, joint laxity will be higher with hormonal fluctuations, and this will lead to certain measurable changes in the running biomechanics, and we may be able to use that support to improve that. How do we plan to do this in lab? We basically are expecting that we will have a screening session where we will take some sort of blood markers and determine where in the cycle the participant is. And then in those different phases in the cycle, have people measure the joint laxity measurements. So basically make an understanding of whether those hormone fluctuations are relating to joint laxity changes. And then have them perform a running task in a lab with ground reaction forces measured and motion capture to determine whether things change in the different phases. And then if those changes are noticed, then we will have them potentially run with an intervention to determine if we can influence that. This is a study that is currently being planned and done with Hannah, who's a visiting student in our lab. She's in her undergrad just finishing up, and she's starting a master's in the spring. This will be her main focus of the master's thesis. And while we're starting with one intervention, we also want to make sure that we're holistic and prospective in this approach. So we will also measure certain extra variables that may not be tested just for her thesis purposes, but will be collected so that we can later go back to it and draw any sorts of associations with the results that we're seeing. And then we also plan to prospectively track some of the other variables that may not be something that we measure on a daily basis in our biomechanics lab, but definitely think contribute to the injury risk in female athletes. And that's my second example that I quickly want to walk everyone through. So prospective tracking, I've taken the example of training load as a variable. We include things like readiness, training type, duration, RPE, and pain in that, and basically have a survey that we would essentially send to our female runners that we're tracking prospectively, have them rate all of these different things on different days of their activities, and then keep doing this prospectively over months and hopefully years. And what we can do from that is I've just put together an example of some simulated data, pretending to be 3 runners that are logging these things. And in this case, just pretending to be a half marathon. In my half marathon training prep, disclaimer, I hate running and I do not run, so that would never be me, but that's okay. We are pretending that that is happening. And basically what we can do from there, from collecting that data, is capture something called training load or calculate that using the session duration and then the session RPE that these participants report. And from there, we plan to get something like acute and chronic workload over a span of days. And these are calculated again using some weighted moving averages. Essentially what this is doing is giving more importance to your most recent sessions in order to understand whether you're increasing or decreasing your risk of getting injured. So then we would do a graph like this. We would plot the load on the y-axis over their days of training on the x-axis, and we can see the acute one obviously has more jumps and bumps in it because it is an acute, more short-term measure. The chronic one is more flattened out because of that longer average. But what we can do from there is then calculate something called a workload ratio, which has been shown in some studies in other sports to be related to injury incidents. Hasn't been tracked in running yet at this scale. So what we're gonna do is hopefully take a variable like this, take some of the thresholds that are measured, and then try to understand whether that workload ratio can help us track prospective injury risk. So we start plotting that for our different participants, participant 2, and then participant 3, which we can see, okay, there are some red flags here with participant 3 going on, and maybe we'll capture that in this acute chronic workload ratio. And then prospectively tracking other things like pain and injury incidents may help us to start answering those questions about what really leads to an injury. So this part of the project is going to be something that a summer student, Summer, who's joining us this year, will be working on. And she is a Bachelor of Health Science student at Queen's, and this will be her project for the next few months. But just going back to the big picture framework. My goal here today was to share what I'm thinking of doing in my postdoc work, how I'm thinking of doing that, and what the thought process behind it is to get some feedback. But the long-term goal ultimately is to build a database that is the most extensive, comprehensive, prospective database that we can go back to and analyze to hopefully better understand the female athlete in terms of injury risk. And with that, I would like to thank everyone that has in some capacity been involved in my PhD or postdoc work, and thank you for your attention and time. With that, the floor is open for questions. Who would like to start us off?
I just have a question, not about thinking, but just about when you removed the carbon fiber plate, how did you keep the stack height the same, or did it influence the stack height of the shoe?
No, it did not influence the stack height of the shoe. The carbon fiber plate is very, very thin. It was like a couple millimeters from what I remember. So no, the glue pretty much takes up for that.
Okay.
Stack height wasn't like substantially influenced. Yeah.
I wanna get like a philosophical debate going on. Hopefully none of the Nike guys are on the computer, but if you talk to Matt Nurse, he'll say, we know exactly what's going on with these shoes. our mandate is not to share these data. Why would we share these data? Like, why, you know, but what do you think about that? I mean, the shoe companies are, their opinion. I mean, they're looking at us laughing in academia. They're like, you guys are running around trying to figure out how these shoes work. Meanwhile, we know exactly how these damn things work. Like, what do you say to Matt Nurse when he says that?
Well, in general, I'll say this, not specifically to Matt Nurse.
He's
But-
probably on.
Hi, Matt. I think, so there's definitely people that are on either side of that argument. Some people will say, no, they have no clue, they don't know what is going on. We're trying to understand it, and then there's people that say, of course they know, why are we spending time doing this? I think I'm somewhere in the middle of that. I think we had literature that suggested what happens when we increase the bending stiffness, what happens when we increase softness. There was data to support certain changes that we've seen in shoes. There was argument or debate over the fact that is the flat plate really essential or optimal for running performance. So some of these modifications seem like they're definitely driven by the data that we knew and understood. But I think it also happened to be a happy coincidence with the combination where now that we're doing studies where we're isolating the different features, we're finding certain things that happen individually, but you put them together and it's not what you expect. So I think that's the part they don't know and didn't expect. That's my opinion.
Do you think academics should be doing research on these shoes?
Well, I did it, yes, you should have.
Right, so now I have some specific questions. So did the EVA shoe change the weight of the shoe?
By 23 grams.
Okay, so not significant. You never had a no plate EVA condition,
No,
If you did, would you expected that shoe to have 4%? Like would you expect to see sort of this additive effect with the plate and the EVA? Where we're equal 4% gains?
I think we have studies already now that are showing that. So there are studies that have taken the plate out, the EVA. There's like no plate plus EVA, no plate plus FIBA, and then plate plus EVA and plate plus FIBA. And there's this cool diagram that shows the magnitude, exactly what happens. And I forget if it's the additive effect is smaller than the individual effects or if it's the opposite. Mike or Bill or someone, if you remember what that is. I think the combined effect of it is smaller than the individual effects. Right? It's not that you have 1.8 and 2.2 and the combined is 1.8 plus 2.2, it's a little bit lower than that. That was a big question I always had to address in my reviews. Why didn't you have an only EVA condition? My goal was to basically compare going from an original to a no plate. So what is the effect of just the plate? And then going from an original to an EVA, what is the isolated effect of the midsole? And I thought if I did both of them together, it would be a bit too complicated.
Yes.
Nice thought. I'm wondering about the joint laxity. So how do you measure it? Is there like specific parameters to measure it and the differences in the run?
So the way to measure joint laxity is there's a device, basically joint laxity measurement devices. There's certain different ones. So there's manual devices that you can basically like a therapist or a sports med expert would basically move your leg forward and back and like manipulate it manually to measure certain changes and movements. And those are done using like goniometers and a Lachman test or a Lach meter. And then there's a little bit more of a systematic way of measuring it using something called a KT arthrometer. So arthrometers in general, which then give you numbers and are less manual, like they have certain methodologies that you have to follow and will give you the objective measurement of how much your joint laxity is changing. they don't make that device anymore, and there's a new one that's really, really expensive, so we're trying to figure out how we're gonna calculate joint laxity and measure it in our study. Bill, do you have a question about that?
Yeah, so the joint laxity is like a passive measurement.
Mhm.
So how do you correlate or attribute that passive laxity to like a dynamic laxity when they're actually running? Is what I'm asking, like, does that, if you have high laxity passively, do you also have high laxity here on these active as well, or muscles are active?
So the way it's been done so far in the studies, and these studies have looked at counter movement jumps, landing tasks, and cutting tasks. They've essentially related the passive laxity to increases in dynamic laxity by measuring changes in knee valgus and variables like abduction moment, and saying, okay, if this increases, if there's more knee valgus, that we're seeing it because of that change in laxity. That's how it's been related so far. That's the way I was planning to do it. But I'm not sure if someone has done dynamic laxity measurements, and I should look at that.
So it's basically change in the properties of the ligament that are
Correct.
holding.
Yes, and mostly because of the changes in collagen, because of the hormonal fluctuations.
So how do you want to correlate this? Like, okay, you measure laxity and then do you measure the biomechanics of running
Yes,
and then decide whether laxity is helping or not helping?
correct, yes.
Okay, so how do you decide? How would we decide?
So there are certain studies in running specifically that have related variables like increased hip and knee abduction moments to prospectively developing injuries. While the sample sizes are very small, there's like 12 participants in that one study that has related this. They did find the highest correlation with these two biomechanical variables during running. That then went on to, or the participants that showed this went on to develop PFPS and a few other running related injuries.
Right, and then some.
So the four big running injuries that you showed were stress fractures, patellofemoral syndrome, and IT band.
Yes, ITBS.
So tell me what the link is between the joint laxity that you're gonna be measuring and some of those very common injuries. Like, what's the probable mechanism?
My thinking right now is based on the knee laxity increasing, knee anterior tibial translation increasing, to then seeing measurable changes during running in that knee abduction moment. And then being able to understand whether prospectively those people that have bigger changes during running end up developing injuries.
Have people shown other effects of hormone fluctuations, like on tendon and things like that?
I don't remember coming across studies that looked at the tendon specifically. I'm looking at Hannah because she also helped me with this review, and I don't think we came across anything that. This hormone piece of the puzzle is just starting to become really popular, and people are starting to look a lot at it, but there's not a lot of research from maybe like 2 or 3 years before that.
Has anybody, has anybody done a study, maybe you couldn't do this because of the ionizing radiation, but has anybody done a study doing body composition, looking at bone, lean mass, and DEXA, like longitudinally and at the same time measured changes in these hormones?
I think I've seen a couple of studies, but they've done things related to pre and post menopause.
Yeah.
So not in that one phase of the, or like not in that young healthy population. Yeah.
Can you tell people what the faster fee is and what the results are about you?
So yeah, sure. So there's a Puma shoe called the Fast R3, which is the successor of the Fast R2. And that shoe essentially was designed based on some biomechanical data collected in labs. So they had runners come into the lab, perform some running tasks, and then collected pressure data and some moments, and then fed that into the simulation to basically optimize certain features of the shoe. And then based on that data, when the shoe was designed, it's further improved running performance by about 3 point something% compared to that previous one and the Nike Alpha Fly, which already improved running performance more than the 4%. So yes, it's a further performance improving running shoe that Puma has made with data-driven insights.
So that shoe is better at performance than the Vaporfly.
Correct.
Okay, by how much?
3.6%, thank you.
And that was done in collaboration with the university, all the modeling, simulations and that?
Correct.
That's your answer why you should work with universities.
What?
That's your answer why big brands should work with universities. Get another 3.5%.
Oh, okay.
Thank you.
Now my question.
So they would, so we're saying that this, you're saying that Puma would not have done this work, and they would not have the shoe without them doing the collaboration with the university?
I'm saying not sure.
Wait,
Oh, that was his comment. He gets to answer that.
Yes.
no, I mean, that would be cool, that would be encouraging.
Right.
I just wanna make sure that that's what happened.
Well, that's how it was presented.
Mhm.
The question I have is, with regards to all this oxygen consumption or running economy, you would think you see this in muscle activity. Why are we not seeing this in muscle activity?
We had lots of discussions about this, and I'm surprised that's your question to me because you were part of those discussions. But so we did multiple studies at this point that were using footwear that should hopefully, or that we expected would change muscle activation and then influence energy cost of running. But all those studies, I would say there were like 3 studies we did not find consistent changes in muscle activation with footwear. I don't think that means nothing is going on at the muscle level. I think there's something, but surface EMG and just simply looking at the activation level may not be the answer to the question. I think it's more to do with the velocities at which these muscles are working and the muscle tendon units, something about the shortening velocities, and there's some data out there with ultrasound, and I think that may be a more promising avenue to look at when trying to understand what goes on at the muscle level.
So you think it's there, we're just not measuring the right thing?
That's what I think. For me, I collected 4 muscles with surface EMG. It's just such a tough equipment to work with that I ended up with my 2 that had good data. And out of my 15 participants, I had good data for 10 people and then good data for 12 people in the other muscle. So.
I may try an explanation.
Mm-hmm.
I mean, if you look at the EMG data, you add them up and down and no change. But what you have not done is individually look at these results and compare them with the results for the energy measurement.
Mm-hmm.
Because it could be, for instance, that some people have differences that are non-responders, and some people have no differences that are responders or something like that.
Mm-hmm.
And the second point that I would like to make is the human muscle skeletal system is an overdetermined system. You have more muscles than you need.
Mm-hmm.
That means you have an infinite number of solutions possible to solve a certain case.
Yes.
And you have not looked at
Correct.
that bridge between the 2.
Yes. I agree with the second point more so than the first, because the first one where I think we also tried looking at that, but at some point in my PhD, we said, okay, let's see if there are responders and non-responders, and the thing was like with 15 participants, 14 out of 15 showed a change in energy costs of running in the same direction, but maybe 3 out of 15 in the energy, in the muscle activation showed an increase or decrease that related to that. So that part, I think we did try to answer, and we didn't find any sort of connection between these functional groups or responders, but the second part is part of my limitations for sure in the paper as well, is that these are only two muscles. Because of whatever reason, I wasn't able to include the data for the other two muscles, and I didn't even measure things further up the chain. And like you said, it's an overdetermined system. There may be a different solution than just increasing or simply decreasing muscle activation, which I did not look at. So that could definitely be.
But if you would want to go further in this question, would you think that artificial intelligence would help?
I think that would be an interesting place to look, because we've done some studies where we have looked at machine learning or AI to try and understand whether there are differences where we don't see them, because we go in with certain hypotheses that we would see these changes, but then you feed that into a neural network or you use machine learning and it totally spits out different answers. So I think that would be a cool start.
Yes, please.
How do you think different parts of the body will experience more stress or loading based on the increase in abduction from knee valgus?
Say that again?
So knee valgus causes like biomechanical changes, and then if you were to draw like an FBD or something, how would other parts of like, let's say the lower leg or lower body experience more loading and stress and therefore like lead to injury?
I'm not sure, to be honest. Like, having not looked at the actual data collected during these kind of movements and like seeing those changes, right now, I don't think I have the answer to what I would expect. It's funny how the NID group is asking me the most questions.
Any other question for us? Yes, please.
So how do energy, metabolic energy cost per session? Is it taken or
Not the VO2 max, it is measured using here. This is why you put backup slides. So energy cost of running calculated using the energy expenditure in kilocalories per minute, and then the running speed and also the body mass. So it's kilojoules per kilometer per kilogram.
So who's using, which part of the body is using the energy?
At the end of the day, and I've had discussions with Jared Fletcher on this, because he's like, he could not believe that we found no differences in muscle activation, because he says it has to be coming from the muscles. There's nothing else that is using energy at that point to perform that task. So I'm not sure, to be honest.
But you know things like force length relationship, force velocity relationship, you know that there's the importance of rate dependence of force development and energetic costs. And none of that stuff can you measure with acquisition.
No,
So why would you expect EMG to show you anything?
right, I agree. I think where we started was trying to understand the simple questions, where because there was nothing to even go off of at the beginning, my first step was, okay, muscle activation must change. Now that I've seen that doesn't change, my next step would be to do that.
We have a question.
So in general, Peter, what do you think makes someone a responder or non-responder therapy?
Or
What makes someone a responder or not responder? I think one of the things would be how that EFT is tuned to their anatomy, or in general, whether someone, like, we know certain things with bending stiffness. Lighter people cannot make the most of certain levels of bending stiffness because they may not be able to utilize that to their optimal. We know certain things about also body mass or certain running styles with foot strike patterns playing into softer midsoles versus harder midsoles. So I think a combination of anatomy, their running style, and things like that, I think would come together to influence if someone's a non-responder or responder. The interesting thing is with these new features, mostly all of my 15 participants were a responder in the sense that they had the lowest energy cost in the Vaporfly. I verbally just asked them to rate their most preferred shoe. And on average, this wasn't part of my analysis, but just out of curiosity, on average, everyone preferred the EVA version more than the original. They felt more stable in it, but we also know that stability or the best stability does not account to best performance. So all that to say, in this case, I didn't really have enough data to start figuring out the responder versus non-responder situation, but those are the variables I think would play into it.
Okay, with that, then Ashna, no? Where's, oh, I'm sorry. Then I'm sorry.
Just a comment about the EMG measurements. In my career, I have been involved in probably more than 1,000 studies that measure EMG. And whenever it was related to something that was performance or actual real movement related, we never found results. So that is final point.
I like that comment.
Okay,
Thank you.
more questions? No? No? So now, with that, it's